episode, and today we will talk about volcanoes. Who doesn't love talking about volcanoes? They are some of the most fascinating natural features on the Earth's planet. But before we do, let us review a little bit about the rock cycle and specifically about igneous rocks. So we began the rock cycles talking about magma coming towards the Earth's surface. So that magma has liquid properties, but it can solidify below the Earth's surface intrusively, or it can solidify at the Earth's surface extrusively. So intrusive or extrusively. When that happens, it is going to be a driver of texture, and texture is a word that we use to describe igneous rocks. So relating to an intrusive igneous rock formation, we use the term phaneritic. And so a phaneritic texture is when you have grain sizes that are more easily identifiable. As an example of an intrusive igneous rock that's common is granite. And so granite contains the minerals biotite, quartz, and some type of feldspar. Pink granites have potassium feldspar. And so those three minerals are solidifying out of a body of magma at some temperatures defined by the Bowen's reaction series. And they have a lot of time and they have a slower cooling process that allows them to grow bigger and bigger below the surface. So when you look at a piece of granite, for example, you can easily identify the different colors, and those different colors represent different minerals, which is different than the extrusive version of granite, which is called rhyolite. And in rhyolite, it still has ample parts of biotite and quartz and feldspars. But in this situation, when you have an extrusive igneous rock form from the solidification of magma, it forms very quickly. And so those grains don't have necessarily the same amount of time to form. And so when you look at a piece of rhyolite, it may appear completely pink in color, despite having the same mineralogy as a granite. So intrusive versus extrusive. Intrusive is phaneritic texture. Extrusive is aphanitic texture. And we start with talking about the solidification of magma, and we looked at some igneous intrusive features in the last lecture. So we talked about how dikes and sills can form below the surface and are part of that solidification cooling process. But we haven't talked about extrusive igneous features, and that's where we're headed today. So specifically, when we talk about magma exiting the Earth's surface, we talk in terms of volcanoes and volcanic activity. So I direct your attention to the screen here, and I'm going to ask you, what is odd about this picture? And so if you look closely in the left-hand corner of the screen, you can see a kid, and he's just kind of like standing there with his arms crossed, looking at the lava flow. So my question for you then is, how can he be standing at the foot of this lava flow and not be panicked, right? So we answer that question by asking another question and looking at why some volcanoes are explosive and others are not. So the picture on the right-hand side of the screen is the classic textbook example of a Hawaiian Island lava flow. The lava is coming down probably Kilauea. There's a house in there. But other than the lava kind of like flowing around the house, you don't have to be too concerned about how quickly it's flowing, because it's going to move at a much slower pace. So as long as you're not in close proximities to the heat, then you're probably not in a whole lot of danger. Opposite of that, if you look to the volcanic event on the left-hand side of the screen, we're looking at the Mount St Helens eruption of May 18th, 1980. And in this situation, Mount St Helens is considered to be an explosive volcano. And the difference between the two, just visually, like if you look at the right versus the picture on the left, you can see that the picture on the right has mafic lava, and the picture on the left has felsic lava. And so we define those terms earlier in the semester. So something that is felsic has greater than 50% of silica. We said that SiO2 represents quartz, and we said that things that are felsic are light in color. So white and pink are examples. Opposite of that, something that is mafic has lesser amounts of silica and therefore is going to be replaced by heavier minerals like iron and magnesium and manganese. And so when we look at mafic examples of igneous rocks, they are often dark green, gray, black, and even red. So the percentage of silica content within a body of magma is going to determine if the volcano is violent versus non-violent. Non-violent is on the right, violent is on the left. We also call this non-explosive versus explosive volcanism. So your biggest and baddest volcanoes in the world, Mount Fugi, Mount Rainier, Kilimanjaro, Krakatoa, those volcanoes are all explosive volcanoes. And when you were to see them on TV, all you'd have to notice is that white ash cloud as an indicator. That white ash cloud indicates to you, the viewer at home, that it is a felsic event. So the magma chamber has high amounts of silica content. And silica, SiO2, has a really strong covalent bond. So you're imagining the magma trying to work its way up to the Earth's surface, and it does so slowly. And because it's moving so slowly, it is trapping gases. And so when we talk about silica-rich magma, we say that it has a high viscosity or a high resistance to flow. So that magma just does not want to move up the throat of that magma chamber. And so trapping gases, and then eventually you end up with a major eruption event occur. Opposite of that is like the Hawaiian Islands. And so mafic magma has a low viscosity, it's a low resistance to flow, so it's easily flowing at the Earth's surface. And so you don't really need to be too alarmed if you're in the presence of such. And so that's why even on the Hawaiian Islands, you can walk up to the edge of a lava flow and be able to witness the process of solidification right before your eyes. So ultimately, it has to do with the percentage of silica in the magma. And what we also learned from Bowen's reaction series is that felsic magmas are going to be closer to the Earth's surface. So we said that quartz, SiO2, is going to solidify at 800 degrees C, whereas something like olivine, that's mafic, is going to solidify at 1400 degrees C. So your felsic chamber is usually always shallower than your mafic magma chamber, which is considerably deeper into the Earth's surface. Once in a while, you can get the mixing of those two magma chambers, but we don't see that frequently. One place where it is possible is the island of Iceland, and that's interesting because when we talk about divergent plate boundaries, so these plates that are moving apart from one another, we usually associate them with the ocean, and we usually associate them then with basaltic type of crust. Basalt is an aphanitic, extrusive igneous rock. And so when you have Iceland that's being spread apart, you would expect that you would have the majority of your island producing non-violent eruptions. But in fact, you see the presence of about 33 active volcanoes on that island. And when I say active, I mean explosive. So there is a presence of felsic magma on the island. And truly, that's still a big question mark for volcanologists to answer. I want to go ahead and put these terms on the screen because you'll probably have a quiz or exam question about them. So again, to define viscosity, viscosity is the resistance to flow. Magma with low viscosity flows easily. So mafic magma is an example of magma that has a low viscosity. And the lower the viscosity means the less silica content that it has. So again, when you see the big ash cloud volcanoes erupting, then the ash cloud gives you a clue that there's a higher amount of silica because silica is white or light in color. And silica leads to more eruptive volcanoes because the silica is a really strong covalent bond. It doesn't want to move up the throat of that volcano. It has a high resistance. So you end up with explosivity ultimately. And I wanted, again, to put Bowen's reaction series on the screen. We've talked about it a little bit. When we're looking at Bowen's reaction series, we're kind of thinking of it as an upside down Y. So you want to think of the surface of 800 degrees being closer to to the surface of the Earth, and 1400 being closer to the outer core of the Earth where the magma is going to originate. And so temperature is going to increase with overall depth, and your mafic magma chambers are then going to be deeper than those that are felsic. And once in a while, you can get mixing between the two. And with these violent versus non-violent eruptions, again, they're visually different. And I want that to be the take-home message is you are now becoming a citizen scientist. And so perhaps you're going to go on vacation and visit volcanoes, or perhaps you're simply watching TV and there's been a major volcanic eruption. We've mentioned a little bit how volcano events can disrupt air traffic and air travel. So these, as a natural disaster, are pretty important to have some awareness of, and I'm glad that you've taken this geology class to learn more. So even looking at the screen now, you can tell the difference between a violent versus a non-violent event. The violent event is on the right this time, and the non-violent event is on the left. So if you see a picture on the screen and it's Mount Fugi and you're traveling to Japan, you're going to have to probably look to see if flights are even going to be passable. When we talk about the difference between violent and non-violent eruptions, we look for different features also in the landscape. And so this is kind of fun if you're traveling to different volcanoes, as I do, to look for these different features. So if it is a violent eruption, for sure you're going to see the ash cloud. And of course, the ash is going to go up into the air and then fall down onto the Earth's surface. In addition, sometimes, because when we talk about violent eruptions, we're talking about huge volcanoes. So these volcanoes can be more than 4,000 feet tall. And so likely, if they're 4,000 feet tall, they're going to be glaciated. And so you end up with an eruption underneath a volcano. That volcano is going to mix with the water. And when that happens, you end up with something called a pyroclastic flow. And that's in the picture that you see on the left. So you've had your volcanic eruption happen. The volcanic ash has mixed with the meltwater from the glacier and has flown down gradient. So you end up with a fan that's called a pyroclastic flow. And they can be quite devastating. You can imagine if there was a city, a town, or people at the base of that volcano, they can be a problem. They can be devastating. For non-violent eruption, we can look for specific terms called a'a, pohoihoi, and pillow basalts. And these are all for sure features that you would see if you visit the Hawaiian Islands. But for sure you can see them on other landscapes too. So in and around Yellowstone National Park, for sure in places like Iceland. So in this case, a'a, pohoihoi, those are Hawaiian terms. And a'a comes from the idea that if you are trying to walk on this landscape, you are going to hurt your feet because the rocks are so jagged, as you can see in these pictures. So the idea is that you have lava, and that lava is flowing at the Earth's surface, and because there might be something in its path, it kind of like backs up on itself. So instead of being able to flow gently in one direction or the other, instead the surface might be uneven, so you end up with this piling of magma at the Earth's surface that will eventually begin to cool. So you end up with this very jagged landscape that obviously looks like you're on the surface of the moon in a lot of capacities. And if it's not a'a, it's also going to be pohoihoi. All of these situations are relating to mafic types of magma. And you know that now because the magma that you're seeing on the screen is dark gray or black in color. So for pohoihoi, you end up with these ropey-like textures where lava is flowing down the flank of the volcano, and then it is very quickly cooling, and you end up with these beautiful lobe-like structures that kind of looks like rope. And the cool thing is that if you are in the area of the volcano, you can then map the direction of the flow. So you can find the source of where the magma was coming from. And that's a lot of fun to do. And geologists do that so that they can figure out the volume of a specific event related to another event. And here is our map of Iceland. We'll remember that in this location, the Eurasian plate is moving away from the North American plate at a rate of about 1 inch per year, or 13 miles per million years. So as you have that rift, you're allowing for a conduit of magma to come more easily to the Earth's surface. So get your mind around this. Iceland then is the location of 33 active volcanoes, and the island is about the size of Virginia. What? That's crazy. Iceland, that is the size of Virginia, has 33 active volcanoes on it. So pretty much anywhere you go in the landscape, you're going to see a recent volcano that can be either explosive or non-explosive. Most of them are explosive. And you can see pretty much every single volcanic feature on the island that you'd have to search the whole world to find. So it's a very impressive place for volcanology. The gray area on this picture here to the left is very just basic schematic. It's showing you locations of some of those major volcanoes. I may have mentioned to you a volcano by the name of Katla, and Katla is down here on the Atlantic Ocean in the what we call the South Icelandic Seismic Zone, and that is going to be a very devastating eruption when that takes place. The last time that Katla erupted was in 1918. So we're more than 100 years overdue. Katla is a historic volcano. It's been around for the past 10,000 years. And it erupted 23 times after 874. And it was really like a nuisance to the Vikings, but they wrote a whole lot of sagas about it. So we have a historical record about the impact of Katla, and Katla has been pretty nasty over time. So that's the big volcano to watch on the island. So since we're talking about volcanoes, we need to think about how we organize them in space. And so we give volcanoes different classifications. So there's different types of volcanoes. So I want you to take a look on the screen here with me. And my question to the viewers at home, how are these volcanoes visually different from one another? How are these volcanoes visually different from one another? So you can make some comparison. One of these things is not like the other, right? So you have some things in the scope, the field of the picture that gives you some clues. So you have some trees here. Looks like you have a glacial ice cap on top of this picture over here to the right. And down here you have some trees on top of this volcano. So my question, how are these volcanoes visually different from one another? And hopefully what you're picking up on is first, the size and the scope of them, but second, the sides of the flanking volcanoes tend to be steeper or not. So when we look, when we look at the picture in the upper right-hand corner, this is a picture of Mount Fugi. It's glaciated, and you see that it has steep flanking sides. That's different than when we look at the picture to its left. That is an example of Hawaiian Islands. It has a very gentle slope. So it would take much less effort to climb the volcano on the left than it would on the right. And then the one that's in the center is a very small type of volcano. It's called a cinder cone volcano, but you can get a perspective of how much smaller it is than the one up here in the right-hand corner because of the trees. So let's define these independently, shall we? We shall. So the first is called a shield volcano, and these are classic Hawaiian Island examples. So you have done some studying in this course about the Hawaiian Islands when we started to talk about plate tectonics. And what you learned is that the Hawaiian Islands result from a volcanic hotspot. So you've got a hotspot that's underneath the Pacific plate. Hotspots are stationary. Hotspots have convection cells. And the convection cells are these density-driven systems that bring magma up to the surface. It cools and condenses. So it's a circulatory system. But the hotspot itself remains stationary, and the plate moves over top of it. So that's why you have the Hawaiian Island chain. of volcanoes. So they're all basalt because they're originating under oceanic crust. And because they're basalt, what we know is that they are mafic eruptions, and those mafic eruptions have a low resistance to flow, and so they're non-violent. So when we talk about shield volcanoes, we talk about them being basaltic, we talk about them being mafic, and we talk about very just gentle eruptions that result. So you're imagining the magma's coming to the surface, and then it's just very gently coming out of the central vent of the volcano and gently flowing down the flanks to the ocean. So we see this in the Hawaiian Islands as our textbook example. Now they can be very big, like you can't even see the top of the central vent in this picture. The entire island is considered to be the volcano. So they're massive volcanoes, but the difference is that they just don't have a very steep flanking sides. So the shape of them, the geomorphology, is quite different. So here's your example of your Hawaiian island chain. You've got the main island, and then you've got Maui and Oahu and Kilauea, all in a line here. And you've done some work, as I mentioned, trying to figure out how long it has taken these Hawaiian islands to form. So the Hawaiian Islands are fantastic. If you go there, usually they're always erupting, so you get to see some type of magma coming to the Earth's surface. The next is called a cinder cone volcano, and these are, of the three, these are going to be the least common, but we see these often in Iceland. So in this scenario, what happens is you have magma, and that magma is coming not from the subsurface, but the magma is flowing on the Earth's surface. So you might have something called a fissure eruption, where you have a crack in the landscape, and that crack is close enough to the hot spot that allows magma to work its way to the Earth's surface. So now you get a magma that's flowing laterally at the Earth's surface, and when it does, it comes into contact with water. So it might come into contact with a lake, permafrost, a swamp, ice. But at any rate, when you have this magma flowing at the Earth's surface and it comes into contact with water, you get a one-time steam eruption. These are called Phratic Eruptions. So you get a one-time steam eruption, and it produces this perfect cone formation in the landscape. And so I'm showing you this. This is in a place called Mývatn in Iceland. It's in the north. And so you're looking at these different cones, and you can see the road. So you kind of get a scope of how big they are. They're not very big, but usually what happens is you just don't have one cinder cone eruption. You might have many in an area. So in Mývatn, there's 21 of these, and if you look at them aerially, you can figure out the direction of which the magma was flowing. There's another place in Iceland that's called Rúhallur, and there's 51 of these different craters. And so once they erupt from the steam, they become completely dormant. So you're able to traverse them and walk on them. And it kind of gives you the feeling, especially if you're in Rúhallur, that you're on the moon, because all these different craters, they range in size. So some are quite big, some are quite small, but they for sure dot and scatter the landscape. So just one more thing. So a cinder cone volcano would be considered to be explosive. And you can see how dramatically and quickly they change the landscape. And the last type of volcano is called a composite volcano. And composite volcanoes are really steep. So they're going to have a slope around 33 degrees. And sometimes they can originate as in an area, I should say, around a cinder cone volcano. But usually they're going to have their own magma chamber that's in the subsurface. And usually it's going to be a felsic magma chamber. So we're talking the temperature of the magma is only around 800 degrees C, and it's working its way up towards the surface. And it's going to, that felsic magma is going to move really, really slowly. But as it does, and it comes to the top of the central vent, then you end up with a major eruption. So the magma, because it has a lesser resistance, it has a more resistance to flow, it's not going to flow quickly down the flanks of the volcano. Instead, it's fighting its way to flow. And so that's why you end up with these really, really sharp and steep peaks. So Mount Rainier is an example of this. You're seeing a picture of Mount Rainier on the screen here. This must be summer because she's not too glaciated. And then we can make some comparisons between Mount Rainier on the left and Mount St. Helens on the right. So the last time Mount St. Helens erupted was in 1980 on May 18th. And Mount Rainier has been dormant for more than 100 years. So it's a little bit more of the one to watch. So these are the most active volcanoes within the United States. They are part of the Pacific. They are part of the Pacific coastal range. They're called the Seven Sisters. So there's 7 different volcanoes. If you are able to visit them, they're in Washington, in Oregon, and they're still under a convergent plate boundary. So it's that convergent plate boundary that is supplying the magma for these. So very different than Yellowstone. Yellowstone is still fed by a hot spot. Yellowstone is a good distance away from the convergent plate boundary, but these are fed from the magma that's being generated from the subducting plate melting, essentially, to produce the magma for it. And so that makes sense, right? Because you have, on our west coast, you have a oceanic plate subducting. So the Pacific plate is going underneath the North American plate, and the North American plate is continental crust. And so by that friction, what's happening is that the continental crust that's on top of that subduction zone begins to melt. And so just like the first day of class, continental crust, when we described it, we called it granitic. And we said granitic is a type of felsic phaneritic rock, and that begins to melt. So that's what's generating the source of magma for our volcanoes out west. And so it's interesting to watch them because Mount St. Helens, again, has had some movement over recent years. But really, we're concerned about Mount Rainier maybe a little bit more because Mount Rainier is quite close to the city of Seattle, where millions of people live. If you visit the city, you can, on a clear day, you can see Mount Rainier hanging over. It's a beautiful and magical thing to be able to experience in person. So I hope you get to do that. So when we, again, talk about the biggest and baddest volcanoes, not just on our North American continent, but if we extend it through the Pacific Ring of Fire, this is where some of the other major ones are. So we can see where the Pacific Ring of Fire goes, and you can see that it includes all of Central America. Man, there's some beautiful volcanoes in Guatemala. Costa Rica has 9 active volcanoes. That's a relatively small country too. Throughout South America, and then you can see just all the way through the western part of the Pacific Ocean. So this doesn't even include Hawaii, right? This is just focusing on convergent plate boundaries and how they produce earthquake events. So I just wanted to show you a picture of Mount Fuji, probably one of my favorite volcanoes. I've been able to hike it. I hope that you get to too. It's custom in Japan when you're hiking Mount Fuji that you start at night. So you start at a base camp at night. And the reason why you do is because the goal is to hike to the top of Mount Fuji and to get there for the sunrise. So you're trying to get up the volcano for sunrise. So you leave the base camp around 8 o'clock at night, and then you're trying to arrive as the sun is coming up. And so a lot of times it is quite wet, especially when you're underneath the cloud level, but Mount Fuji Sun's more than a 14,000 foot hike. So once you get above the cloud line, usually the clouds begin to part, the the coldness, the dampness begins to dissipate. You're above the tree line then, and it is spectacular. The other cool thing about hiking Mount Fuji is that it's tradition that in the Japanese culture that you only hike Mount Fuji one time. So there's a lot of elderly people who make the pilgrimage, and it is seen as a pilgrimage. So it's actually quiet when you're walking up the volcano, even though there's thousands of people hiking with you. It's a very serene event. So you get to the top, and then you wait patiently for the sun to rise above the clouds, and then everybody cheers, and there's a chant that is in respect of the volcano. And then after sun has risen, now you walk down and everybody's fully chattering. So I hope you get to see that, and I also hope that you get to see some of these fantastic volcanic features in Iceland. So I mentioned sometimes when you're in the interior of the island, so off the ring road and in the interior, it kind of feels like you're on the moon. So nothing is able to grow. And the reason is because you've got 33 active volcanoes on the island. So you end up with about 25 volcanic eruptions every 100 years. So all that volcanic ash landing onto the surface of the island impedes the growth of most things. The picture down here in the lower right-hand corner shows you what a dual chamber event might look like. So you can see pumice on the bottom, and so that pumice is felsic, light in color, and then on top of that, you can see these scraggly types of basalt, and basalt is mafic. So what we would know about this eruption just by looking at the picture is that the felsic magma chamber erupted first, and that makes sense because it's shallower. And then after a period of time, the second magma chamber erupted. And that second mafic magma chamber is deeper. And so it's able to work its way up to the surface and then flow. This may be a better example over here in the right-hand corner. So you've got pumice on the bottom, and then you've got these basaltic bombs is what they're called. And so they're erupting out of the volcano, cooling, and then falling down to the Earth's surface. These features are called columnar basalt. So the feature in the middle and the two on the bottom are called columnar basalt. And columnar basalt forms when you have a body of magma that's coming up from the subsurface. And again, it comes into contact with water, but usually the water is going to be cold, or it could be a body of ice. So the magma is coming up from the subsurface, comes into contact with ice or really cold water, and the presence of that is going to slow down the crystallization temperature of the basalt, and so it's going to contract, and it forms these perfect hexagonal patterns. So if you look down in the lower right-hand corner, you're looking down on top of these long and tall columns, and they're perfect hexagons. So it's really kind of a situation where you're dealing a lot with physics. And probably most important for me in my research is thinking in terms of pillow basalt. So this is the upper left-hand corner, and they look like pillows. And so how these form is when you have magma that's flowing down the flank of a volcano, and it comes into contact with the ocean in this situation. And so opposite of columnar basalt, instead of having contraction, now you have expansion or inflation. And so these basaltic features are going to form these beautiful pillows. You can see them in real time, like at the Hawaiian Islands, form right before your eyes. And so if we're interested in knowing something about past sea levels, then we would look for these pillows along the edges of the island of Iceland, because they're going to give you an indicator of where the past ocean level used to be. And of course, there's fancy math that has to go into it. So you have to consider uplift and subsidence and erosion. But ultimately, you get to figure out where the ocean level used to be. And again, if you're interested in changes of climate over time, that includes the changes of the position of sea level. Cool stuff, huh? And We're not going to talk about glaciers in this lecture because we're focused on volcanoes, but one thing that was really surprising to me when I went to Iceland the first time, and I was so excited to see glaciers, I expected them to be pristine. I expected them to be like these completely white scenarios, but Iceland, that is home to 33 active volcanoes, that has 25 volcanic episodes every 100 years, produces a lot of volcanic ash. So the ash goes up and then falls back down onto the surface of the glaciers. And so the volcanic ash gets entrained as they move. And I just show you these two pictures because, in fact, what you're seeing is the volcanic ash. So they don't look completely white. Instead, they have the volcanic ash that's mixed in with them. The last thing that we're going to talk about is similar to recurrence intervals and similar to magnitude when we talked about earthquakes. The question is, how do we make some comparison between volcanic events and volcanic energy? And so volcanologists use an index that's called the Volcanic Explosivity Index. And this considers a lot of different things, including the volume of what is leaving the volcano, the explosivity, the length of the eruption, and the amount of material that is injected into the atmosphere. So we're thinking in terms of how tall the ash cloud is going up into the atmosphere. So on the screen is an example of the VEI, Volcanic Explosivity Index, and it goes from 0, which is a non-explosive event, to an 8, which is the most explosive. On the y-axis, you're seeing the general description at the top, and then you're seeing the other indicators, the other characteristics of a volcano. And so the great thing about the VEI is not only can we do this for modern events, but we can go back in geologic time and make some estimations about the intensity of eruptions, because things like tephra is kind of like another word for ash. We can estimate the amount of tephra in an area. We can estimate based on if it's felsic versus mafic, if it is what type of an eruption we expect it to be, and then we can even make some predictions about how tall that ash cloud was. So the VEI is great because we can use it as a key to monitor volcanoes at present, but we can also make some estimations about them in the past. As an example, on Iceland, there was a volcano called Aska, and Aska erupted in 1755. And there is pretty good written record of how tall they thought the ash cloud was. And scientists, volcanologists, were able then to model what they expected it to look like. And when they did that, they estimated the ash cloud to be 42 miles tall. So this massive ash cloud going out and exceeding the stratosphere. And moreover, when we look at where the ash goes, it goes up and comes down for sure. But if an ash cloud is that tall, it gets carried in the wind circulation system. So the Aska 1755 event produced enough ash that it crossed 700 miles across the ocean, headed to Europe, and you can find it there still today at about 1 centimeter in thickness. So it gives us a perspective of how big and intense that event was in historic time. And with that, we're interested in making some comparisons, and everybody's usually interested in Yellowstone, and so that's why I include this. It's called a super volcano because it is historically been so big. So you're looking on the right with color, and color indicates some large eruption material events. So we're looking in terms of the orange being greater than 1,000 square kilometers. And then, so that's your red and your oranges, and then your yellow to your blues get smaller and smaller. So if we make some comparisons between Yellowstone and some of the biggest and baddest volcanoes on the planet, you can see that Yellowstone ranks right up there. So Yellowstone at Huckleberry Ridge 2.1 million years ago produced 2,450 square kilometers of volcanic material. So tephra, ash, pumice, that type. So a massive amount of area was covered. And then we can look to what happened more recently. So the Yellowstone at Mesa Falls, 1.3 million years ago, produced 280 square kilometers of volcanic ash. So you're thinking of a radius of an area of 300 kilometers that is covered with this volume of tephra. So these crazy intense events. Of course, we talk about Yellowstone erupting. Probably won't be in our lifetimes, but it'll probably be a pretty big event. It would show up on this record for sure. So I think I am going to talk a little bit more about some of these major events that have happened in some of the places that you might travel to, hopefully. So you might have heard of Mount Vesuvius. And so Mount Vesuvius is in Italy, and Mount Vesuvius erupted in 79 AD. And so when it erupted, it completely buried a city called Pompeii. And so in these pictures that you see at the bottom of the screen, you can see the cast of people. And so these people are in place that were living in 79 AD prior to the volcanic eruption. And you can notice that they're lying in place. So probably what happened is that because when you have a volcanic event, you have gases that go into the atmosphere, for sure carbon dioxide, but you can also end up with sulfuric dioxide and carbon monoxide. And so likely, hopefully, what happened is that the people were kind of put to sleep before they got buried by great depths of volcanic ash. And when I'm talking about great depths, we can talk about anywhere between 10 feet and 20 feet falling on top of the city of Pompeii. Like the city was completely buried and eventually uncovered by archaeologists. So you can see this if you go to Pompeii. Additionally, there's a place that's called Ashfall Fossil Beds, and that is in the great state of Nebraska. So if you're ever driving out west on Highway 80 and going across Nebraska, this is in western Nebraska. And a similar situation occurred. You may be familiar with Devil's Tower. Devil's Tower is in Wyoming. It is no longer an active volcano, but it did erupt. And likely the ash from this Devil's Tower eruption was carried to the Ashfall fossil beds and buried. What you're seeing in this picture is rhinos. So this is from the Miocene. So the interior part of the United States was kind of like a great savanna. And so you had things like rhinos and hippos. And this particular area of Ashfall fossil bed was thought to be a lake. And so you had all of these hippos and rhinos and camels kind of collecting at a lake, and then they got buried. But it's a beautiful collection of complete skeletal features if you're interested in fossils. So I think I'm going to stop here today. You've been a wonderful audience. I get really excited when I talk about volcanoes. I hope you bring to me some of your favorite volcanic experiences. Hopefully you've done some hiking, and if not, hopefully you aspire to do that sometime in the near future. So have a great day, and I will be back at you.